Welcome, everybody. It seems like there are several of you returning, so I'm excited to talk with you today. My presentation for this morning is figuring out what's the matter with the universe. We actually have some problems with our understanding of the universe, and one of the biggest ones is matter relating to mass. So a little bit about me. I did my PhD at Purdue, so I was active in SMAP several years ago. And I have always really liked astrophysics, the sky, constellations. So that's one of my Halloween costumes from when I was probably about your age. I'm an experimental astroparticle physicist. Those are three pretty big words. I have always wondered what things are made of, how things work. Yes, astroparticle means the particles in space and the physics of them, how they move, the real nature of what the stuff is. And then I'm experimental, so I build machines that try and figure out and answer these questions. So as a physicist, I'm trying to figure out what the universe is made of, how things work. Astroparticle is specifically parts of the universe, particles from space. And then I build experiments to find out what those are. I am a professor at Bucknell University. So West Lafayette, Indiana is somewhere around here, if you can see my cursor. And Bucknell is in the center of Pennsylvania. We're deep in these little hills, rolling hills. We've got a lovely river as well. There's a lot of parallels between Lewisburg, Pennsylvania, and West Lafayette, Indiana. It's a great place for undergrads. We have 3,800 students approximately. Our acceptance rate is 32%. It's about a tenth of the size of Purdue. We have 14 physics faculty, again, about a tenth of the size of Purdue. There are 4 experimentalists, of which I'm one. We have 2 in the field of dark matter and 2 in the field of biophysics. We have 4 observational astronomers and a really nice observatory on campus. There are actually 6 female professors, which is a huge fraction. Physics as a field largely dominated by men, so this is a unique department for physics. We also have a lot of resources on campus. We have a machine shop with 2 technicians. They can build nearly anything. And then if you want to be the one building stuff yourself, we have these engineering maker spaces. You walk in, you can use a 3D printer, you can use a laser cutter. There are a lot of opportunities to be creative and build and make and explore. But then going into what I've been talking about, astroparticle physics, we are concerned about dark matter. And I'm here to talk about what do we know about it? How do we know it's there? Who wants to tell me what they already know about dark matter? Feel free to unmute, put answers in the chat.
It can't be detected.
Well, I'm trying to detect it, and right now it hasn't been, that's true. We'll get into that. We'll try to figure out how it can't be detected, and then how I'm trying to detect it. That's a great answer. So one of the ways we know it's there is from how objects in space are moving. In terms of galaxies, stars are moving around our galaxies. In the case of the sun, we are moving around the Milky Way galaxy. And when we look into space, into these galaxies, we can tell how much matter is there based on the stars and the dust. So we know the mass, which is important for gravity. The gravity of stuff inside an orbit pulls on stars to keep them in orbits. And that mass that is pulling these stars in, the mass affects the velocity of the stars. So if we go from the center of a galaxy outward, the amount of stuff in the bubble within a certain radius gets larger. So the stars are able to move faster. However, we get to the edge of the galaxy and there's not as much stuff. So we should expect at some point those outermost stars to go slower. we don't see that. We see that the stars are maintaining really fast velocities, which is only possible if there's a lot of mass. So, as an activity, let's go to breakout rooms and have you decide how much dark matter needs to be in the whirlpool galaxy. Actually, just before we go to breakout rooms, I'm going to describe a little bit this activity. We sent you a link to a Colab notebook, and this is Python, which is a coding language that we physicists use for our analysis. So first of all, coding is usually a bunch of commands, and not all commands are available all the time. So we have to import some of those commands in what are known as libraries. So we're just going to do that. I give you some text to sort of outline this. You're free to read this if you haven't already. And here is a picture of the whirlpool galaxy that I took with SLU. Who's familiar with SLU? I see a couple nods and hands. Excellent. Yes. So this is something that you're able to see yourself, and this is with the SLU telescopes. And when we see galaxies, we notice there's a central bulge. There's a lot of stars in this central part, and that's very spherical. And then in the case of these galaxies, these spiral galaxies, they're actually quite pancake shaped. This one is full on in front of us. So for the whirlpool galaxy, you're not able to see how thin it is. It's a disk. So there are two main components to these galaxies for matter we can see, the central bulge and then the disk. And these are measured. I took some data from this resource. So there's this cell, and you can run cells by either clicking the run button or shift enter on your computer. So yeah, the components of the galaxy are the bulge, the stars, but we know there's dark matter in there too. And dark matter is actually going to be a bubble. It's going to be a spherical bubble around the entire galaxy. So now we can go into breakout rooms, and you're going to be changing the amount of dark matter. If we didn't have dark matter, you can see that the way the rotation curve should fit, or should be, does not fit the data that we see. So your job is to change this amount of dark matter until this gray line fits the data. It should be a pretty good fit. And then you get to calculate how much of this whirlpool galaxy's mass needs to be in dark matter. So what fraction is dark matter compared to all of the mass in the galaxy? So let's go to breakout rooms, and you can play with this yourself and discover how much dark matter needs to be in the whirlpool galaxy.
Do you need help getting Colab up and running?
I think one of the best way is one of us shared our screen and then maybe show them a little bit how we are going to run the code and how we are going to do that.
Sure, we can do that. We can all work on it together. Charles, do you want to share your screen, or should I?
Sure, I can share my screen. Can you, all of you see where my cursor and then my notebook here, right? So as Abby mentioned earlier, this is just a code that named Python. When you are going to the college, you're gonna learn a lot of different computer programming language. So the Python is one of the most popular language we are going to use to help us physicists to do the experiment. So basically, this notebook is a bunch of sections that you can run for the computer coding. For this activity, actually, we are going to change one of the parameters in the code so that we are going to do some small experiment or maybe some small guess about how much dark matter are going to be in that galaxy. So before we are going to move that to the main topic, we have to run some several cells. Oh my God. Okay. Never mind about all those notifications. Just tell me it's written by someone else. Okay, so basically, these are the descriptions. If you are like to read a little bit about the galaxies and rotation curve, you can read by themselves. So right now we're just going to jump to the code and do some activities. Okay, so here you can see, as Ivy mentioned, if we put dark matter mass as 0, like you see, like here, if you put nothing here, but you look at the rotation curve. Okay, so what is a rotation curve? So the rotation curve is basically a 2D plot. On the x-axis is the radius to the center of the to this galaxy. And then on the y-axis is the velocity. So what's this velocity? This velocity is the how quickly, how fast the object is moving in the space. For example, if our Earth is rotating around the sun with a speed around several kilometers per second, and also Mars is rotating around the sun with several kilometers per second. So with the distance to the sun, for example, Earth is only 1 AU, which is closer, and the Mars is like 2 AU, or Mars is several AUs to the sun, which is longer. So for example, on this rotation curve, Earth is going to be here, and the Mars is going to be here. So basically, how you can understand this plot is the further you are away from the center of the galaxy, basically the velocity should be different when you are in the different location around the galaxies. So this line, this dashed line, is the real data which we are measuring how much the mass rotate, the velocity of those mass are when you are in a different location to that galaxies. And then those color lines are the different theoretical predictions and measurements about different objects, how their velocity are in the different location. And then adding them together, we should get a same line about this dashed line. But in reality, you can see if you change the dark matter to 0, which is this blue line, which if there's nothing dark matter here, you can see our final line, the gray line here, doesn't fit with the real data, which means here we should do some change to this blue line so that the combined data together should have the similar result with this experimental measured data. Okay, so let's do it right now. So here we started with 0. We didn't see the graph was fitting. Now let's change the graph. Let's change the dark matter mass to 10 to the 40. 10 to the 40. Let's just see how much we have.
So Charles, I actually have an idea. If we're all going to be working on this together, it might be really fun to we can run it at one just to see what happens. And then if everyone can put a number to try in the chat, then we can just go through each number and see how they each affect it. So it says numbers between 1 and 50. So if everybody can put some number between 1 and 50 in the chat, let's get a wide range of numbers so we can see different effects. And then we can go through and try each of them and see what's the closest.
Yeah, great. And also we can have a little bit of competition and see who's the closest to our final result.
Yeah.
Oh, nice. I have
Well,
several.
competition's fun.
Couple seconds, we're gonna start our competition. I'm gonna go from the lowest number to the highest number and see the result. Okay, let's start it with 18, which was 18. So all you need to do is come here and change number. So we change dark matter number mass to be. So now you can see 18. Wow. 18 is pretty much close in my opinion, because at the beginning of the rotation curve, you can see, so now after you change the dark matter mass to 18, you will see the blue lines, they change to a slope line instead of a horizontal flat line here. When you change the 18, that means there are 18 times 10 to the 40 solar mass in the galaxy, which means they are distributed in the different locations. And then the distribution of 18 will change to a little bit for the result. Okay, I'm gonna say 18 is pretty much close because you see that at the beginning all the lines are fitting, but still there's a little bit of disagreement in the end. Okay, let's jump to the next. So I really like 18. Let's see how 20 works.
18 looks really good. That was a good guess.
Okay, 20.
20 is pretty close to 18, so it should be
Wow,
similar.
20 is pretty close to 18, but I may favor 20 a little bit. Sorry for the people who put 18 because
Yeah, I think 20 is winning so far.
yeah, I think 20 is winning so far because in the end you will see like 20 is slightly closer to the curve. But I think we still can do better. Let's try for the next number. I'm gonna go from the lowest to the highest. Next number is 35. Wow,
Oh, 35 is really good.
35 is really good. I think there's only something like a little bit disagreement at the 4 kiloparsecs.
Yeah, I
And
think it might just be slightly too high, if anything.
yes,
maybe just a little bit.
Yeah, you can see the entire curve is like running like above of the experimental data, but still, I think I like 35 over 20, but we still need to try 50.
Yeah, let's see what happens.
Wow,
Oh yeah, 50 is too
50
much.
is a little bit above the curve, but still.
What we learned so far is that the correct amount is somewhere between 20 and 35, but a little bit closer to 35. So if you guys can now put guesses that's in that range, so we can narrow down even more, that'd be great. So somewhere between like 20 and 35.
And bulge plus. Yes.
Ah, okay, okay.
So that is a piece that you can add based on the example code for how this is so Python, these are really big numbers. You can, if you'd like, plug each of those numbers that's in the mass of this, the mass of that into your calculator, or you can make Python do that calculation. And we do that by, instead of writing out the really long numbers, with variables. So we've named those numbers mbulge, mstar, and dark matter.
So it's following this example code where you have variable 1, which is dark matter, and then divided by all the other variables added up. So the mass of the bulge, the mass of the stars, and the mass of dark matter.
This is nearly exactly how we do this. We have the measured data, we have a model of the different parts, and then we optimize, or we fit the total amount to that data. And this is exactly how we measure how much dark matter is in different structures. And especially for physicists, astrophysicists, these Python notebooks, as they're called, of what we do with using Python to make sense of the universe and data. In terms of other coding languages, sometimes there's something called MATLAB. There's a couple simulation, C++, Java, but really Python has taken over as the main coding language to know recently. And one of the first things you usually do with Python is exactly the example there. You can use print comments, and with single quotes is just whatever your message you want the computer to tell you.
If you want to save the work that you've done in the notebook, in the top left, you should see an area to be able to save a copy to your Google Drive. So then you can mess with it later.
Well, let's sum up what that was. What fraction of the galaxy's mass needed to be dark matter? I know what we found in Breakout Room 1. Who wants to tell me about Breakout Room 2? Yes, in Breakout Room 1, we got about 70%, 72%. Who was in Breakout Room 2? Within the chat, we have one data point, but as a scientist, it's better to have more data points. The paper that I cited had it at about 68%, but in my simplifying some aspects of the model, the 70%, 71, 72% is very close to 68%. Within that gives us an idea of our uncertainty on that measurement. And exactly, so way more than half of the galaxy has to be in this dark matter stuff. And we find that on the whole, the universe has finite energy. Energy can't be created or destroyed. There's something called dark energy, which is sort of how space is expanding. But in terms of the stuff in the galaxy, or in the universe, we have nearly 5 times more dark matter than this ordinary matter, regular stuff that we know about. And we know about this based on the patterns of where galaxies are since the Big Bang and how they're moving, how stars and stuff are moving. And this exercise on the rotation curves of galaxies lets us know within individual galaxies how much dark matter there is, which varies a lot between galaxies. Just on the whole, there's about 5 times more dark matter than ordinary matter. Well, how about we discuss this a little further? What are things made of? What's the smallest thing you can think of? Give you a little time to think. Oh yeah, we've got atoms, we've got an electron, subatomic particles. So within atoms, quarks. Somebody knows about quarks. And leptons. So I'm going to talk about these elementary particles. So based on our squirrel, or in this case, my pet rabbit, a hair is made up of what's known as keratin. And hair is these strands of keratin molecules. Molecules are made up of atoms, but atoms are made up of other little bits. So electrons are definitely very small particles. And of the list, I think electrons are actually the smallest compared to quarks. You can see this is the mass in those weird GeV, MeV units that we use, but 0.5 is smaller than 2 or 4. And so electrons are probably the smallest particle you can think of, well, except for light. Light can behave as a particle. Within the nucleus, we do have subatomic particles such as the proton and neutron, but we know from other particle experiments, some that I have not built, but work with a lot of people who have built these, figured out that each of the protons and neutrons have 3 aspects of quarks. So pretty much everything we know of is made up of these 3 particles in some combination. If you give a little extra energy, you get these, you get some heavier versions of these. So a muon is a heavier version of an electron. And we're going to come back to muons. There's these things called bosons and fermions. They act a little differently, but light can be considered a particle. That energy can be balled up in a location, and the energy doesn't form mass for a photon, but it's still a packet of energy in the form of a photon. And photons are important because they interact with everything here. Photons will interact with every piece of particles that we know of. Dark matter does not. Why doesn't dark matter interact? That is something we don't quite know. That's a great question, Greg, in the chat. Is dark matter not made of particles? We do expect it to be made of some type of particles, but that particle is not in this list right now. And that's what I, as an astroparticle physicist, am trying to look for. So then, how do we make the invisible visible? Dark matter's all around us. We know it's gravity. You've simulated how much mass needs to be in a galaxy for all that gravity we need. And we don't see it. It doesn't reflect, absorb, or emit light. Everything in the universe that we know of regular particles interacts with light somehow, just not dark matter. And then the weak force is those W's and Z bosons. It's a way that nuclear reactions happen. So we're somewhat familiar with the weak force, and maybe dark matter can interact that way. So here's a bit of an animation. A dark matter particle will come in, hit an atom, that atom will move. When atoms move, they create light. So in a way, we are trying to make dark matter, which doesn't interact with light, still cause a chain reaction that ends up with light. Because again, we're very good at measuring light and seeing and understanding our world through light. So now I want to turn it over to my laboratory, as we are in Bucknell, and that's where I'm sitting right now. So now you can see the space where I work every day. I've got a nice corner of the basement with some good lower parts of the windows. And it's a bit of a mess because we're physicists working. I'll have a lab clean out day towards the end of the summer. But I've got a bench with a lot of tools, and this is where we can make circuits that power electronics. We're making a dark box, so a black box where we can put our light sensors and learn how they work. We've got a bunch of tools. I've got a soldering station. So with electronics, they need to be connected with wires, and we do that with soldering them. I've got a hood in case I need to use any chemicals, but I don't expect to use it. I'm in the process of building a particle detector, so we've got some of the pieces laid out that my students and I this summer are in the process of building. And then this box holds 4 detectors already. These are muon detectors, going back to the heavy form of the electron. Particles from space sometimes interact strongly with our atmosphere. And in that case, there's so much energy that they can create muons. These are 4 panels stacked. So the muon goes through all 4 of these panels. It interacts with the atoms in the plastic. Those atoms create light, which is funneled to these light detectors. So we've got 4 light detectors, and these are the electronics that control it. So I can turn them on and ramp up the voltage. This is about 6 times more voltage than usually comes out of your wall. And that light turns into these pulses. So all 4 of them, seeing these light pulses, are how we measure the muons coming down from space. You can't make a lot of measurements just from visualizing this. So we continue with wires to this little box, which talks to this computer. And this box counts the pulses that those 4 detectors are putting out. And we are able to open a Colab notebook, import that data that is saved to the computer, just like you loaded the data for the rotation curve. And we can do an analysis on the muons that are coming from space. In the future, we will have a particle detector that can do more than just muons. But in this moment, we are interested in measuring how space particles are affecting the atmosphere right here at Bucknell University in the form of muons. Who has questions or wants to see a little more around here?
Professor Abby, I have a question. You have the paddles arranged on shelves, one on top of the other. What would the difference be if you spread them out, let's say across the width of the room or even the width of campus?
So if we spread them out the width of campus, we would be able to, if each of them sees a pulse at the same time, get an idea of the size of a shower. So the particles hitting the air cause a chain reaction that kind of spreads out. So we can see the size of a shower that way. There's some detectors in Chile that are up to a couple kilometers that are able to see these showers. And so 4 isn't a great number for that. However, by having them stacked, I can look at one muon multiple times. So it will be able to travel through all 4 of those detector paddles. I'll know that it's moving straight down, so it came from the atmosphere and didn't come from other nuclear reactions in our everyday materials. We are surrounded by things that undergo nuclear reactions, but at very low levels. It's just the way that regular matter works.
Like, I was kind of going back to what we were talking about earlier, but like, how can we measure mass of, or the observable mass of these galaxies when we can't like physically measure them, like, when they're so far away?
That's an excellent question. Yeah, we can't make a large scale and weigh the galaxies. However, we can look at, we know our sun very well. And a lot of these stars have a lot of processes very similar to the sun. Based on the solar system, which you saw, there's a squirrel's worth of mass compared to the entire Earth. Dark matter is not a big player in solar systems. The mass of the sun is pretty much the only thing holding the Earth in orbit. So we know the mass of the sun based on how the Earth moves around the sun, and it actually relates to the brightness. So we can make a relationship between the brightness of the sun and the mass of the sun from us moving around it, and then extrapolate that to galaxies. That's an excellent question. So then there is one last part that I wanted to talk about. I also work in Italy. This detector that I'm building in this lab, it's one room. It's small. We have our detector setup, which is going to go in the frame. And then the electric pulses are going to go to my computer. And we should be able to do some science with the particles that are up here. However, I won't be able to see dark matter. We've done experiments of a size that can fit in this room already back in the early 2000s. We didn't see dark matter. So we put limits on what dark matter could be. And we need the scientific community to come together to build larger experiments. So I work on the XENONnT dark matter detector, which is under a mountain in central Italy. There are 250 scientists from around the world, from Japan, Germany, Italy, the US. Those are some of the main players. And we built this experiment to use xenon as our nucleus for dark matter to hit, and then the xenon lights up. Xenon is a particularly nice element because it doesn't have some of those radioactive processes that other atoms do. So it's a very stable, it's an inert gas, it's a noble element. We just have xenon. It's also heavy. So if dark matter is particles that are somewhat heavy, it is a very good target to try and get dark matter to hit. And only the central part of this detector is xenon. We have our light sensors. You can somewhat see, there's on the top and the bottom. Particle comes in, creates light in the xenon. We see it. Those electrical pulses, which you just saw small scale in my lab, are sent to this giant's computer to be saved. We have our office space to work. And we have 2 more floors in this building, which is a mile underground. And this is where we can hold a lot of xenon and process it. And we can also purify it. We need these floors for handling the xenon and making sure that it's purely xenon for the dark matter to hit. We also put it inside a huge water tank. Water also creates light when it's hit, specifically by muons. Up here, you saw how fast the oscilloscope, it's called an oscilloscope, or how many times per second we saw these muon pulses, these pulses from the muons going through. When you go a mile underground, that happens once per hour. That way, we don't burden our electronics with seeing extra light from these muons. We still get them once per hour, so we build this giant shielding tank. It also gets rid of radioactive things just from like you and me standing outside. We have this buffer of water to protect the xenon experiment. Because yes, even we are made up of some atoms that are radioactive in very small amounts, and you're completely safe. Isa asked, could dark matter affect our daily lives? No. Not that we can really tell. It's a huge question, like, what is the universe made of? What is this dark matter? Why don't we understand our universe that we're living in? If we understood dark matter and understood our universe better, we might be able to make better predictions about the life cycle of stars, how our sun is doing, because we're concerned about our sun, but we probably don't need to worry about it for the next billion years. He's also asked, like, what did I study? Would you mind speaking up and expanding on your question of what did I study?
Like, what was your like career path, I mean, to get like to this point or this type of topic to investigate or study?
I thought I wanted to be an engineer. I really enjoy taking things apart, putting them back together, fixing things, making stuff, being creative with my hands. However, I went to a bachelor's university that I went to Boston College for my undergraduate or bachelor's degree, and they at the time didn't have an engineering program. So I thought physics was about the next best thing. I can do grad school in engineering, and there is a lot of flip-flop between bachelor's and graduate work, where engineers do graduate work in physics or physicists do graduate work in engineers. But I fell in love with physics. I did research as an undergraduate. I had a great graduate student I was working with, a good mentor in the faculty members that I worked with, and I wanted to continue this. And to an extent, I still do a lot of engineering, but it's problems that don't immediately have answers. So I have to do the problem solving. I have to figure out how physics allows me to build something that does what I need it to do. And that will be the only instrument in the world, because I built it the way that I needed it. And so I figured that out around my third year of undergrad and decided to go to graduate school. That's when I got into Purdue. And at that point, I actually didn't know much about dark matter. I didn't really know about dark matter until the first or second year of my undergraduate, when I took a high energy astrophysics class. So, but that was more towards the astronomy side and doing the rotation curves of galaxies, that there's a lot of mass in the universe. It's probably particles in matter, but it doesn't interact with light at all. So that's the extent of dark matter that we know. It wasn't until I got to Purdue that I met Raphael Lang, my advisor. He gave a really interesting talk about trying to look for this dark matter as particles, that it's passing through the Earth at all times. We don't know whether the whole squirrel's worth of mass is in one giant particle that travels through the Earth very rarely, or whether it's spread out in lots of very, very tiny particles. It could be much smaller than an electron. It could be much larger. It could be as large as a squirrel. So it could actually also be as large as the Earth, focused into a point. We do know that it's not black holes. Black holes even give off some light signatures. And that's the extent of the individual parts of dark matter that we know, and we're building experiments trying to figure out what that is. So I talked to Raphael at Purdue. He took me on as a graduate student, and that's what I've been doing for several years now. After I got my PhD, I did a postdoc in San Diego with one of my collaborators, San Diego, California. And then this past year, I got this faculty position at Bucknell University. It was great to meet you all, and thank you so much for your questions.